In this lecture, we'll discuss the transformation of the coordinates and time, which is associated with a switch from one inertial reference frame to another. So first, let's recap what happens in the classical physics. So if we have a reference frame K and another reference frame K prime, which moves with some velocity with respect to K, so let's say, to be definite, that it moves in the direction of the x-axis. And also, for simplicity, let's assume that at some time, at t equals 0, the k and k prime coincide. So the origins are at the same point, and all the axes are aligned. So then, in classical physics, it's easy to see that the coordinate x is expressed through x prime through simply adding vt, right? So the distance here then is equal to vt. Now, nothing happens to y and z, and because time is absolute in classical physics, then t is equal to t prime. So this is called the Galilean transformation. Now, as we discussed in the previous lecture, this transformation is incompatible with the postulates of special relativity. We have learned, in particular, that the interval between any two events, so event 1, some coordinates r1, t1, and event 2, coordinates r2, t2, the interval s squared, which is equal to c squared t2 minus t1 squared minus r2 minus r1 squared, is the same when measured in any inertial reference frame. So you can use t1, t2, r1, r2, or you can use the primed variables, primed coordinates in time in k prime, and s squared and s prime squared is the same. So in order to figure out how the coordinates transform, let's pick the following two events. Event number 1 is simply the location of the origins of the two reference frames, k and k prime, at the time when they coincide. So call this t equals 0, right? This is what we assumed here. So let's call that t equals 0 at the origin where O and O prime coincide. Let's call it event 1. And event 2 is simply an arbitrary event. So in reference frame K, the coordinates are r and t, and in reference frame K prime, the coordinates of that event is r prime t prime. This can be any event. So anything happens at some point and some time. So what we want to figure out is what is the relation between these two coordinates. So they should transform through each other, but not according to the Galilean transformation, which obviously does not respect the invariance of the interval. So the invariance of the interval tells us exactly that ct squared minus r squared should be equal to ct prime squared minus r prime squared. So what kind of transformation is this. Now if we had a plus sign here, this would be a simple rotation in four-dimensional spacetime, which we know very well how to construct the transformation matrices. Those would just involve the trigonometric sine and cosine functions. Now here the sign is different. The sign for the time coordinate is opposite to the sign of the three spatial coordinates. Now the set of transformations that leaves the interval invariant obviously includes the transformations of the kind where t is unchanged, but the spatial coordinates are subject to a simple rotation in three-dimensional spacetime. So this will leave the r squared invariant. So r squared is equal to r prime squared. So this is a simple rotation in 3D. But this is not the transformation that we want. So the transformation that we want involves transformation from k to k prime, where one is moving with respect to another. So although this rotation in 3D preserves the interval and is compatible with everything, it's not the most general kind. Now what we want is a transformation that involves time and space at the same time. So let's consider the transformation of the following structure. Let's consider the transformation where x and t mix together through a hyperbolic rotation. We'll write the formula shortly, while y and z are unchanged. So this transformation, because y and z are unchanged, will correspond to ct squared minus x squared equal to ct prime squared minus x prime squared. So let's figure out what kind of transformation this is. Well, first of all, just as we parameterize simple rotation with sine and cosine functions, it's easy to see that this transformation can be parameterized using trigonometric hyperbolic functions. So let's write it in the following way. So x equals x prime times hyperbolic cosine of a parameter, that's what we'll call zeta, plus ct prime hyperbolic sine of zeta, and ct equals a similar expression where the sine and cosine are interchanged. Using the trigonometric expression that cosh squared zeta minus sinh squared zeta equal 1, we can easily see that this transformation respects the invariance of the interval. Now, what does this transformation represent? Consider the origin of reference frame k prime. So this point has coordinates r prime equals 0, including x prime equals 0. So if we use this in the coordinate transformations, we'll find x equals ct prime hyperbolic sine zeta, and ct equals ct prime cosh zeta. So x and t here are the coordinates and time of the observation of the origin of k prime in the reference frame k. Okay? So we can in fact find the velocity of the origin of k prime by taking x over ct. So ct prime cancels. So this becomes the hyperbolic tangent of zeta. Now x over t is the velocity of the origin of k prime with respect to k. So this is v over c. So we find that this transformation here corresponds to the situation where the origin of k prime is moving in reference frame k with velocity v that is parametrized by this parameter zeta, and the y and z coordinates are not affected. So this is obviously the transformation corresponding to the situation that we need, namely that k prime is moving with velocity v with respect to k. Now this also tells you how the parameter zeta is related to the velocity v. So now we can get rid of it in the transformation formulas here and express the transformation directly through the velocity. Now that we have the hyperbolic tangent, we can easily find the cosh and sinh. So cosh is 1 over 1 minus squared tangent, which becomes 1 over square root 1 minus v squared over c squared. Now the hyperbolic sine is cosh zeta times tangent zeta, which becomes v over c divided by the square root. So if we substitute these in the transformation here, we'll find the following expressions. So x equals x prime plus vt prime divided by the square root, and t equals t prime plus v over c squared x prime divided by 1 over divided by the square root. Okay, so this is now the transformation where everything is clear. There's no parameter zeta that we need to determine. Here everything is expressed in closed form. So this tells you what happens to x prime and t prime when you re-express them through the coordinates in reference frame k. Now if we wanted the inverse transformation, to transform from the unprimed to primed coordinates, we could, of course, take the transformation matrix and invert it, or we could realize that we can simply interchange the k and k prime and change v to minus v. So the inverse transformation amounts to simply replacing v by minus v. Now let's also write a matrix representation of this transformation. So let's write this for column vector ct, x, y, and z. So those are the four-dimensional coordinates. So there's going to be a 4 by 4 matrix here, and there's a column vector ct prime, x prime, y prime, z prime. So here y and z mind their own business, so nothing happens to them, so they also don't get admixed to either t or x. Now it's conventional to introduce the notation gamma as 1 over square root. So because we're writing for ct, we're going to have gamma here, and then for the time here, we're going to have gamma v over c, and there's a gamma v over c here. So this transformation matrix, we can call it L, encodes the transformation from k prime to k. Now let's consider some examples. So the first example, let's take a ruler at rest in one of the reference frames. So let's say it's a ruler at rest in k, and the ruler is aligned with the x-axis. So the endpoints of the ruler are at x1 and x2. Now, from the point of view of the observer in k prime, the ruler is moving. So the question is, what will be the length of the ruler observed from reference frame k prime? Or in other words, what's the length of the moving ruler? Okay? So what does it mean that we measure a length of a moving object? Well, that means that we want to find x2 prime minus x1 prime such that they're measured at the same time in reference frame k prime. Okay? So in other words, we perform a simultaneous measurement of the coordinates of the two ends of the ruler in reference frame k prime. That's what by definition is the length of a moving ruler. Simultaneous observation of the two ends. Okay? Now, if we use the transformation formulas here and substitute t1 prime equal t2 prime, so we can then write that, just write x2 minus x1. So in the right-hand side, the terms with t prime will cancel because t1 prime is equal to t2 prime. So we'll simply find x2 prime minus x1 prime divided by the square root. Okay? Now, this is L, and that is L prime. So we find L equals L prime divided by square root 1 minus v squared over c squared, or L prime, that's what we want, is L times the square root. Okay. So the length of the moving ruler, L prime, is less than the length of the ruler in its own rest frame by the square root. This is called the Lorentz contraction. Where the length of the moving object appears to be shorter than its length in its own rest frame. Okay? So here's another example. Let's take a clock at rest in reference frame k prime. So it's just attached to the origin or some other point of k prime and moving with it. So the clock shows proper time, as we discussed before, proper time delta t prime. Now we want to compare it with the time in reference frame k. Okay, so how do we do it? Well, again, apply the coordinate transformation. Now, because the clock is at rest in k prime, that means x1 prime equals x2 prime. The clock just doesn't move; it's at the same place all the time. So if we then write delta t, which is t2 minus t1, and use the transformation formula, so the terms with x prime will cancel. So here we'll find delta t prime divided by the square root. Or, in other words, we can also write delta t prime equals delta t times the square root. So this is less than delta t. So the clock in the moving reference frame, where it's at rest, delta t prime, when compared to stationary clocks, is counting slower by this square root. This is called a time dilation. Let us finally work out the velocity addition rule. So we're interested in the following. So we have a reference frame K and a reference frame K prime, which moves with velocity v in the x direction with respect to K. We know the velocity v prime of a body in the reference frame K prime, and we would like to know what is the velocity of this object in K. So in classical mechanics, we simply add v to v prime. So v equals v prime plus v. But in relativistic physics, this is no longer true. So to work out this addition rule, we come back to the coordinate and time transformation. So as you remember, we have x equals x prime plus vt prime divided by the square root, and t equals t prime plus v over c squared x prime over the square root. And we also have y equals y prime and z equals z prime. Now, to find the velocities in K, we can take the differential versions of these relations and then simply divide dx by dt. That will give us vx and so forth. So in differential form, add the differentials here. Same thing here. And then vx is by definition dx by dt. So we take this and divide by this, substitute here. So we have dx prime plus v dt prime divided by dt prime plus v over c squared dx prime. The square root has cancelled. Now we divide by dt prime. So we have dx prime by dt prime plus v divided by 1 plus v over c squared dx prime by dt prime. But dx prime by dt prime is just by definition vx prime. So we find vx prime plus v over 1 plus v times vx over c squared. Now similarly for vy, it's dy by dt. So substitute dy prime times the square root that comes from the denominator. And here I have dt prime plus v over c squared dx prime. Again, divide by dt prime. So we have vy prime times the square root. And in the denominator, 1 plus vx prime over c squared. And a similar expression for vz. The space-time transformation corresponding to switching from one inertial reference frame to another that's moving with some velocity with respect to the first one is called a Lorentz boost. Now if we look at the expressions for for Vx, Vy, and Vz, we'll notice that if Vx prime and V, capital V and V prime are not parallel, meaning if V prime has Y and or Z components, then the way V and V prime appear on the right-hand side of this expression are asymmetric. You can't just interchange V prime and V. You'll get a different result. This is a manifestation of the fact that two Lorentz boosts along different spatial directions do not commute. The result of two boosts generally depends on the order in which you perform them. This concludes this segment on the Lorentz transformations.